Hello everyone, this is our last topic for the course, polar coordinates. So remember there's two topics that you won't be tested on, but I'll summarize the little review of these two topics for you. The parametric equations, which we just got finished studying, and now polar coordinates. Recall there's a document posted, final exam topics, study only these topics. And you can see in part 3 we've got parametric equations and polar coordinates, so telling you exactly what to expect. And after we're done with this lesson, I'll have a video that'll review these two topics for us. And there's homework regarding these two topics listed at the bottom of the page here. There's a parametric equations homework sheet, and there is some problems from Mr. Brown's book regarding polar coordinates. So obviously we'd suggest you do those problems. So to talk about polar coordinates, there is actually polar graph paper that I posted in the parametric equations and polar coordinates handouts folder. And this is what it looks like. What it has is concentric circles representing what we refer to as the radius, and these radial lines, okay, the angles. And the idea behind polar coordinates is to take a point in the rectangular system. So an XY ordered pair, which is in rectangular form, and to be able to transform it in both directions, so go to rectangular to polar, polar to rectangular, and describe the same point with a radius and an angle. So R represents the radius and theta the angle or the direction. Okay, and this is our polar form. So in the Cartesian system, if you consider, let's say, the XY coordinate plane, this point here, instead of describing it by an XY ordered pair, we're going to describe that same point by a distance from the origin to the point, which is going to be the radius, and a direction or the angle off of the x-axis. So that's the idea behind the polar coordinate system. Now if you want to plot points, sometimes they're given in terms of radians. You probably want to change that to degrees. So here, let's say A is 2 and pi is 180 over 6 would be 30 degrees. And then to plot that point, let me get my polar graph paper here, just simply go along the 30-degree radial line. So that's this radial line here, and 2 units. So if you count each concentric circle as 1 unit, this would be the point A, which is 2 units in the 30-degree direction. Oh, also notice on the polar graph paper I have 4 graphs for you. You can Google free polar graph paper and see a variety of them. These are kind of nice because they're labeled with the radial lines in increments of 30 degrees. There's a better one at the bottom if you want to have a more sophisticated graph. This has, further radial lines. Radii are larger, and the radial lines are in 10-degree increments rather than 30 degrees. But in any event, it's there for you. Now the unique thing about polar coordinates and points is that you could have the same representation, or you could have different representations for the same point. First off, to plot the point -2 and 150, that would mean along the 150-degree radial line, which is this line here, we're going to move -2 units. So opposite to the 150 radial line, we're going to move 2 units. So here would be the point B, which is -2 and 150 degrees. But notice that that's the same as saying if we wanted the radius to be positive, then we'd say move 2 units along the 330 degree radial line. So that's kind of interesting, the fact that you have two different representations for the same point. Okay, and then one final point to plot here, -3, -60. So both are negative. -60 means clockwise 60 degrees. So actually along the 300 degree radial line, -3 units. So opposite to 300 is 120, 3 units, 1, 2, 3. That would put us right here. And that would be the point C, which is -3 and -60 degrees. So again, different representations. I didn't put a little c in front of there. Different representations. You could say -3 units along the 300 degree radial line. Or if you wanted both angle and radius positive, you could say +3 units along the 120 degree radial line. Okay, so that's how we plot points, and you don't really have to worry about that. You'll see the examples that we're going to be concerned with. Here's the theory behind the what you might consider as conversion equations. For simplicity, let's just consider a point in the first quadrant of the Cartesian coordinate system. So some arbitrary point here, call it x and y. Again, what we want to do is be able to realize that same point by saying move a distance of r units in a particular direction. Now, to realize the conversion equations, what we could do is just take that point, drop a perpendicular, always to the x-axis, create a reference triangle or a right triangle, and realize that the horizontal leg of this triangle, if this is the point xy, to get there, we'd have to move x units in the x direction, so the horizontal leg is x, and y units in the y direction, so the vertical leg is y. And then let's imagine we're given x and y, and we want to find r and theta. Well, immediately we have that r squared is x squared plus y squared by the Pythagorean theorem. So that'll give us r. And to get theta, if we have x and y, we'll have to involve a trigonometric function with x and y in terms of theta, and the one most commonly used is tangent. So tangent of theta we could say is y over x, or you can even go so far as to say theta is the inverse tangent of y over x. Okay, so that'll give us theta. Alright, so that's a way to get from rectangular to polar. Now, if we're given polar and we want rectangular, that is, we're given r and theta and we want to find x and y, then let's say we're going for x. We'd have to involve a trigonometric function in terms of theta that involves x and r, and that would be adjacent over hypotenuse, so that's the cosine of theta. So the cosine of theta we'd say is x over r. But then basic algebraic manipulation, multiplying both sides by r, we get that r cosine theta is x. So there's a way to get x, knowing r and theta. And similarly, if we want to find y, we'd have to involve a trigonometric function with respect to theta that includes y and r, and that's y is opposite, r is the hypotenuse, so that's a sine function. So sine is y over r. If we manipulate that, we get r sine of theta is y. Okay, so there's the conversion equations. And although on the exam, you could see on the final exam topic sheet that I mentioned earlier, you could see that for polar coordinates, we're just going to be concerned about converting equations in both directions, from rectangular to polar and polar to rectangular. To be complete, let's talk about points. To convert points from polar to rectangular, sometimes you can get away with just plotting the point and using an intuitive observations to determine r and theta. But sometimes you'll have to use the equations. But definitely plotting the point is helpful. I'm going to show both methods. If we consider plotting this point in the Cartesian coordinate system, -3, 0, so okay, in the xy Cartesian coordinate system, because this is x and y, it's mentioned here, convert to polar, rectangular is given, would just be 3 units along the negative x-axis, -3, and that would be our point. Now what you can imagine doing is superimposing the polar coordinate system on this graph. That is, you can consider that's really 3 concentric circles, right, a radius of 3, and change the axes to be in terms of degrees, 0, 90, 180, 270, back to 360 of course, and then you could see that the point can be given by moving 3 units along the 180 degree radial line, and that's all there is to it. So just analytically plotting the point, you can sometimes determine the conversion. Now if you wanted to use the equation method, sometimes they're a little bit more difficult, but you're done right now. I mean, that's it. That's the point. But using the equations, okay, we can get r from x squared plus y squared. So r squared would be x is -3 squared plus y is 0 squared. So r squared is 9. R would be plus or minus 3. And that's significant because you have to know which one do you want. Do you want the, because you could say this is the same as going in the 0 degree direction, -3 units. So therefore we'll get the tangent function out of this. So the tangent theta is y over x. So tangent theta, y is 0, x is -3. So the tangent theta is 0. Alright, so now we're looking for where the tangent is 0. And you could use your calculator, but that's, or look at the graph of the tangent function. It's actually at 0. If you look at the graph of the tangent, at 0 degrees, that's what it looks like. There's an intercept, but then every pi units, this would be 180 degrees. It repeats itself. So that's 0, 180, 360, so on. You can even take the negatives, -180, -360, and so on. So that's what theta is. So theta has a variety of values. So you have to know which one you're looking for. So you really need to plot the point anyway. So if you do take the positive 3, then you'd realize that you need to choose the 180 degree direction, which of course is the same thing. So then from all that, we get the same conclusion, of course. Okay, so for this point, 5 and negative 5 radical 3, let's make a sketch in the Cartesian plane again. It doesn't have to be to scale, it's just make sure you're in the right quadrant. 5, maybe I'll try to make it to scale a little bit. So there's 5 units in the x. And let's see, 5 radical 3 is about 1.7, so 8.5, so negative 8.5, maybe right around here. But again, it's not necessary to make the sketch. So now we're looking for this radius and the angle. And so what we could actually do here, based on the nature of this, to do it analytically, is consider similar triangles. That is, make a right triangle out of this. Okay, and then we have the triangle, and I'll keep it orientated the same way here. Then we have this triangle where we're looking for this radius, R, where this horizontal leg is 5, and the vertical leg is 5 radical 3, because that's what it took to get there, just 5 in the x and negative 5 radical 3 in the y. And then if we compare that to our 30, 60, 90, here's 30, here's 60, 1, 2, and radical 3, you could see that our triangle is just simply 5 times the size of this triangle. And so you could discern that since this hypotenuse is 2, this must be 10. And similarly that the angle must be 60 degrees. So you could see that this is 10, and I guess we'd have to say negative 60, right? And then if you wanted to convert that to something that has a positive angle, that's fine. Or if you couldn't get make that observation about to get the 10, you can call this side x, and you could use proportions, similar triangles. You could say 5 is to x as 5 is to x as 1 is to 2. And then immediately you get x is 10. Okay, or, so that's it for that situation. Okay, just like here, the analytic observation. Or you could use equations. Equations are sometimes a little bit trickier, though. Not for r squared. R squared is always going to be easy. Let's just plug it in. The x value, 5, has to be squared. Y value, negative 5 radical 3, has to be squared. So r squared would be 25 plus. Okay, when you square a product of an integer and a radical, you got to square both of them and multiply. So negative 5 squared is 25, radical 3 squared is 3, so that's 75. So then we get r squared is 100. And again, the choice, positive or negative. 10. That depends on what angle we're going to choose, and the angle is determined by the tangent function. So tangent's y over x. Y is negative 5 radical 3 over x, which is 5. So tangent theta, negative radical 3 over 1. If you wanted the exact value, you know that you'd still have to know you're in quadrant 4, so you plot it. And consider tangent is opposite, negative radical 3 over 1. Immediately, that's your right triangle, 30, 60, 90, and that's 60 degrees. So, therefore, you can discern that, once again, if you're going to go with positive 10, you'd have to go with negative 60 degrees. Okay, so analytically it's a little bit more fun, but equations will always work as well. And now, if you want to go in the opposite direction, that is, convert from polar to rectangular, we're still going to suggest you plot the points, but the equations actually work really well when you have to go in this direction, as we'll see. So 4 and pi, which you might want to change to 4 and 180, right? Okay, so now we have to imagine we're in the polar coordinate system. And here's 180 degrees. We're 4 units in that direction. So then if we imagine superimposing the Cartesian coordinate system on this, that would just simply be the ordered pair of negative 4 and 0, because we're moving negative 4 in the x and 0 in the y. Okay, so then that's the end of the analytic portion for the equation method. Okay, we're going to use calculate x and y as needed, and to calculate x and y, we'll use our conversion equations. That these would be obviously equations you're going to want to write down on your cheat sheet, because on the final exam I want you to treat it as a proctored exam, as will be mentioned in our correspondence in Blackboard and T-Wolf's email. And you get to write anything you want on the back of that table, as I've mentioned before. And please try to adhere to this policy. I'm going to ask you to sign an academic integrity form, because I have noticed, a lot of internet solutions. I'm not naive. It's pretty obvious to me. I've been doing this for 30 years. But in any way, event, write these equations down. And so x is our cosine theta, y is our sine theta. So then these equations always work really easily, because all you have to do is plug in the value of r, which is 4, and the angle, cosine 180. And cosine 180 is negative 1, so that gives negative 4. And then y is our sine of theta. So 4 sine of 180, and the sine of 180 is 0. So then we easily get negative 4, 0 as well. Okay, for 4 and 135, let's try to do it the analytic way and see what happens. Okay, so 135 would be in the second quadrant. This would be 90, 180. This angle, reference angle, would be 45 degrees. Distance to the point is 4 units, so that's r equals 4. There's a little reference triangle. We could use similar triangles, because what we want to find is x and y. So we could use the concept of similar triangles, like like we did earlier. So our triangle is, okay, we know both angles are 45. Hypotenuse is 4. We need x and y. And if we compare that to our standard 45, 45, 90, I'll orientate it the same way. Both legs are 1 and the hypotenuse is radical 2. So now it might take a little gumption to realize, like in the last example on the previous page, it was obvious when we use similar triangles because we just had to multiply by 5. But here it takes a little bit of gumption, like how do you get 4 from the square root of 2? Well, if you're clever, you could say I got to multiply by the square root of 2 to give 2, and then multiply by another 2. So 2 square roots of 2 times square root of 2 will give me the 4. And then each of these would be 2 square roots of 2. But the x would be negative because we're in the negative direction. And the y would be positive. So that takes a little bit of gumption maybe. But to do it by similar triangles, set a proportion. Let's say 4 is to x as radical 2 is to 1. So 4 would be x radical 2. X would be 4 over radical 2. Rationalize, you get 4 radical 2 over 2 is x. Or x is negative 2 radical 2. And then you know, of course, y is the same, so there's no need to repeat that process. And I labeled the x as negative, obviously, because when you got to plot the point anyway. Okay, so that's the analytic way, using the equation method. See, going in this direction, it's really easy with the equations. In the other direction, not so easy because you got to use the tangent and you got to make some choices and stuff. But here it's pretty straightforward because you just plug in what you're given. 4 cosine 135, and then cosine of 135 is negative radical 2 over 2. So that gives negative 2 square roots of 2, and similarly y, our sine of theta. So again, just plug them in. For sine of 135, and sine of 135 is radical 2 over 2, so 2 radical 2, and then of course we get the same point, negative 2 square roots of 2 and 2 square roots of 2. Okay, so that's changing points and the theory behind the polar coordinate system. Again, the meaningful stuff is going to be the rest of the parts of these lectures, because we're going to look at what you're going to be tested on, converting equations in both directions, and then area in polar form. And then after that, we're done with the course. So hopefully you're excited about that. I know I am. And so we'll come back and do either 1 or 2 more parts, and then we'll be finished, and we'll talk about a review for the final and getting you prepared.